So hopefully you can see my slides. My name
Yes.
is Maria Stone, and I just put a few things here, hoping to be open for collaborations that might come from attending this workshop, as it was noted in the agenda of the workshop itself. My thesis is Supermassive Black Holes, their host galaxies and environments. I'm currently a doctoral student at University of Turku in Finland. And actually, I'm a mature student, and um, I have studied biology in my undergrad, and then by getting involved in astrobiology, evolved into extragalactic researcher. Um, my interest in radio frequencies came from this internship I did at NASA, and I guess maybe you can see it somehow. I can, sorry, there you go. At NASA, I was surveying and analyzing different equipment, including large radio dishes that dealt with any type of research or flights happening on that site in order to assess how they worked and what impact they had on health, and then to come up with correct regulations according to the state and government rules for everybody, not just the people who operate the aircraft, but also visitors or cleaning personnel. And I kept thinking, how are these antennas used for astronomy research? And why not do it by, learn it by doing a project, and why not with this amazing instrument, which is ALMA, and the rest is her story. The plan today is to introduce the interesting aspects and the important aspects of AGN environment, and kind of the frame of reference that I come from, which is optical and near infrared, and then to kind of walk through you and be transparent how it is to come up with observing proposal ideas and how they are drafted and later packaged into a full proposal to be submitted. And in this case, it is done in synergy with Muse observations. And obviously, to present my idea for ALMA observation proposal, its significance, and hopefully to get good feedback today or later. The topic of the observing proposal is to obtain matching ALMA observations of quasar hosts to complement Muse data of redshift 3 quasars, which have shown to have extended Lyman alpha emission. And this is an independently conceived project of my project idea, and I hope to find collaborators. So galaxies don't evolve and don't live by themselves. They are surrounded by gas, surrounded by other visible and invisible, so to speak, matter, other entities such as stars, galaxies, etc. And it is important to study the environment to see whether there are any environmental effects on galaxy evolution in general, or if there are any differences, for example, between quasar environments where you have this active supermassive black hole shining, or an inactive galaxy environment where the supermassive black hole is dormant. You can approach the study of environment from different points of view. You can study at different scales, such as large scale structure, or you can study the host galaxy, for example, of a supermassive black hole, where the supermassive black hole resides, to see if there are any coevolution happening or if there are any scaling relations. You can also study circumgalactic medium, which is kind of the immediate region around a galaxy and helps with the recycling of elements. So this is my interest of my doctoral research. What is the role of, in this case, AGN environment in the formation and evolution of galaxies? So to focus on circumgalactic medium, as I said, it's the immediate region around galaxies and quasars. It comprised of gas, but also dust and anything else in the vicinity of a galaxy. And it's diffuse gas. It's often hard to observe because of its low surface brightness. It can be multi-phase, it can be clumpy, but it is a reservoir of energy, of baryons, and a lot can happen there, such as outflows or feedback processes. So we really need to understand what's going on in CGM. Recently, it has been possible to directly image the CGM around bright quasars with MUSE. And here are a few example studies that I cited. On the top, you can see images of MUSE for about 20 objects. And all of the colored area in yellows or orange reds is extended Lyman alpha emission, which belongs to the CGM. And you can't see very well on the top, but on the bottom, the quasar itself, to which CGM of Lyman alpha, traced by Lyman alpha surrounds, is in this black circle. So it's within the PSF of the MUSE. And on the bottom here is a velocity map. So you can see you can have different gas moving at different velocities. And it's interesting to see that there are different structures, different sizes, at least projected, of this extended Lyman alpha emission, in this case, say, imaged in Lyman alpha. So yeah, MUSE is amazing IFS that let us gain so much more information about circumgalactic medium by directly imaging it. So far what we know is that there are these giant Lyman alpha nebulae around quasars, and they are ubiquitous. And some systems do show turbulence due to outflows, and we do observe diverse morphologies. And it's both for radio and radio loud and radio quiet systems. There are some differences, but okay. What is the Lyman alpha emission line? Well, it's the hydrogen transition, which is in the UV. It's the first hydrogen transition set. And how it's important, you can observe it in CGM, as I showed you with MUSE, by directly imaging it. But you have to remember that CGM has other components there. So it's not, Lyman alpha emission line doesn't perfectly trace the CGM, also because it has some resonance and other properties to it. So you have to keep in mind that even though we have imaged the circumgalactic medium in Lyman alpha emission line, it can be, there are other components to the CGM, and we need to study several tracers of CGM to understand a better picture of what's going on there. Okay, so this last summer, I started studying the CGM around the hot dog. It's a very luminous, obscured quasar at redshift 3. Obscured means there's a lot of dust surrounding this quasar. And I was studying just one object, its MUSE data cube, which imaged the Lyman alpha nebula, the extended Lyman alpha emission around it, trying to find its morphology, its size, its kinematic properties, and how it relates to AGN feedback, etc. And we did find in literature complementary ALMA observations, which help us to understand better our MUSE dataset in a larger context of that hot dog. So here are some things that you can do with MUSE. You can get a spectrum. In red is the hot dog spectrum around Lyman alpha line, and then in blue is just the signal or the flux due to the extended emission. So you can see that there is Lyman alpha emission line coming just from the this extended emission area. Okay. So the beauty of ALMA observations is that they act in a great synergy with these MUSE observations, because MUSE is blind to the host galaxy because it's within the PSF of the MUSE. So while MUSE has a very large field of view and we can see the whole extent of the CGM traced by Lyman alpha, we can't really say anything about the host galaxy itself. And for example, our object that we study was also observed by ALMA and published in Diaz-Santos 2021 paper. They show the spectrum with MUSE of the C2 line, and they were able to study the velocity patterns. They can get the redshift for the molecular class, which is great because the redshifts that we have from other places has a large error bar, and we really need to have a precise redshift for the velocity maps of the Lyman alpha extended emission in a CGM. You can check for turbulence in gas with ALMA observations. You can learn a lot about the host galaxy, such as its mass, its SFR, again, maybe molecular outflows. So this is just an example of what ALMA can provide. So that's where, when I was reading another paper by Arrigone Batalla, which presented 60 plus, so very large sample of MUSE observations of various quasars at redshift 3, I said, why not also complement this with ALMA observations? That way we learn about the host galaxy, but also we can have some statistics. So the impact would be if outflows are present, the host information would be critical to understand AGN role in that galaxy's evolution, such as AGN feedback. We might be able to constrain Lyman alpha emission origins for the CGM, meaning where did the Lyman alpha come from in the CGM? And we can check for signs of AGN effects on the CGM and how it depends on the AGN host properties. And this Tumlinson review in 2017 is a review about CGM if you're interested. So the data sample is again 60 plus quasars published in this paper by Fabrizio Arrigone Batalla entitled QSO Museum. They have all been observed and analyzed, observed with MUSE. So they're ready there to be interpreted with ALMA complementary observations. All of them are around redshift 3. What else? Yeah, these are extended Lyman alpha nebulosities, about 100 kiloparsec from the quasar. Yes.
Maria, sorry to interrupt. You have 3 minutes.
Thank you. I think they published that these ones were predominantly quiescent in kinematics, but there are other redshift 3 quasars which had extended Lyman alpha observations, which had turbulence. So ALMA will allow us to find more information of about the hosts of these quasars. So what are the next steps? For me is to finalize observing proposal technicalities, to double check in the archive what has been observed, what has not been observed. For example, some ALMA data exists in Fan et al. Paper, and Diaz Santos published a few as well. And to communicate with potential collaborators and learn a lot, because I come from optical near-infrared background, but just really interested in this question. ALMA observing, actually you can observe once, if I understand correctly. You can propose an observing proposal once, and the deadline is usually in spring, once a year, I mean. But I have been very happy with the ARC node communication. They're great. Yeah, this year it's due in May. I wanted to write, so what do we really expect with ALMA for this hot dog, for example, for hot dogs or other bright quasars at redshift 3? If we imagine what their host galaxies are, they're probably highly luminous because they are quasars, but a challenge would be to decompose this quasar light versus stellar light. They're highly star forming. Some of them are obscured, or a lot of them are obscured. There may be turbulence, maybe companion galaxies like Roman Fernandez Aranda presented yesterday in his talk. So there are some challenges, but it's also an opportunity to learn new things, what my thesis advisor in master's program used to say. And some technical questions are, for example, in observing proposals, a sample size. Should you go full scale and request time for all of these objects, or maybe select a few? These are some things to consider. So in summary, it's a project to exploit a synergy between MUSE and ALMA observations. MUSE on one side provides the information about the CGM via extended Lyman alpha emission imaging. And it was published in QSO Museum paper by Arrigoni Bataya. But it will be wonderful to get ALMA data to zoom and get information about those quasar host galaxies. And the larger impact would be to understand AGN feedback and coevolution of supermassive black holes and their host galaxies. So the current status is for me to submit the observing proposal, and after some ALMA archival search, double check all of the current observations. And there's even potential in the future to extend this area of research to high Z arena that we talked about last few days in terms of Lyman alpha emission. Thank you.